Thank you everyone for making a nice lull and everything, so we knew when to start. I'm Kaylee Walker, I'm in the physics department, I'm one of the professors, and I'm happy to welcome you to the beginning of the 2025 Nobel Lectures. And our lecturer for this year is Dr. David Tarasick, who's an emeritus, a research scientist emeritus at Environment and Climate Change Canada, but I will leave the introductions to later. I hope that you did see our wonderful posters around and that people availed themselves of lunch. That is one of a couple of our social events as part of the Nobel Lectures. For students and postdocs, there will be a pub night tomorrow evening. So put it in your calendar and there will be more details provided about what time and where tomorrow around the lectures. So as we start off, I need to tell you a little bit about our benefactor. These lectures began in 2003 and have been made possible through the Reginald and Muriel Noble Fund. So I'd like to tell you a little bit about Reginald Noble. He was born on a farm in Clinton, Ontario in 1911. He did a BA in Honors Math and Physics at U of T in 1934, followed by a master's degree in physics specializing in meteorology, also here at U of T. Following that, he was posted to Newfoundland in 1937, was officer in charge at the new District Aviation Service in Montreal, and established a weather forecast office in Halifax, all before he was 30. Between 1940 and 1945, he was in charge of a program seconding almost 400 newly trained meteorologists to all RCAF bases and was the meteorological advisor to the RCAF chief and staff. So after the war, he moved to Toronto, playing an important role in an era of rapid growth at what we now call Environment and Climate Change Canada, including the move to the new building at Downsview, which a number of us know very well. As he moved up in the ranks, starting at what then was called the Meteorological Service of Canada, his illustrious career led him to eventually become Assistant Deputy Minister. Mr. Noble was known as a highly skilled administrator, quiet and full of common sense. And he was also keenly interested in science and happenings at the University of Toronto. So we think he must have enjoyed his time in the Department of Physics, as he left us a very generous bequest to the Atmospheric Physics Group, which has allowed us to establish this lecture series in his memory. So we're all grateful to Reginald Noble for his generosity. We're now going to pass over to Michael Habaruka, who's one of our students, PhD students on the Nobel Planning Committee, for the introduction.
All right, thank you, Professor Walker, and thank you all for being here today. It is a great pleasure to introduce to you all our 2025 Nobel Lecture speaker, Dr. David Tarasick. David began his academic career at Trent University, where he earned a Bachelor's of Science degree in mathematics and physics. He then went to the University of Montreal and earned a master's degree in physics, followed by a PhD in physics at York University. Following his academic studies, David joined Environment and Climate Change Canada, where he worked as a research scientist until he retired last year. During his time at ECCC, he also earned the position of adjunct professor at 3 Ontario universities, the University of Western Ontario from 2007 to 2023, as well as York University in the Department of Earth and Space Science and Engineering in 1996, and the University of Toronto in the Department of Geography since 2014. At Environment and Climate Change Canada, David is perhaps most well known for his work relating to ozone, which I'm sure we'll hear a lot more about today and for the rest of this week. Early in his career, David was also part of the team at Environment and Climate Change Canada, which created the UV index system, a public health tool which is used around the world. And for more than 25 years, he was the scientist responsible for the Canadian ozone sonde network. Through this position, he has been active in many international activities relating to both stratospheric and tropospheric ozone. In particular, projects relating to data quality assessment and standardizing our operating procedures. He has served as the Canadian representative on the NDAC Ozone Sonde Working Group, the assessment of standard operating procedures for ozone sondes, and in 2019, he was elected to the International Commission on Atmospheric Chemistry and Global Pollution. So with that, please join me in giving a very warm welcome to Dr. David Tarasick. How's that for volume? Does that work? A little quiet? How about that? If I speak a little louder, or I don't think I can get it any closer to the mouth. Oh, did you turn it on?
Yes, I'll turn it up a bit.
Okay.
Okay, try now.
How's that? Is that better? Okay, good. All right. Well, you said I could have is this laser pointer?
Yep.
Yeah.
Okay.
Which one? That's the clicker there.
Yeah, that's the laser and then the other two arrows.
Okay. Won't if I start waving this around and you start ducking, then I'll understand that shouldn't do that. So I want to talk about ozone, but I actually want to talk about a larger theme, which I could put in a nutshell as science as entertainment. Because I really think that's the fundamental reason we have science. And I hope to entertain you with that notion today. So I'm starting out with this particular, these images, this juxtaposition of images. This is a picture in the background of the observatory on Mont Blanc in France, one of the higher mountains in the Alps. And it's, I believe, from 1905. That was one of the first ozone observatories. And this, of course, here is a recent picture of the severe ozone depletion, which we sometimes call an ozone hole. The jury is out on whether we can call it an actual ozone hole in the Arctic in 2012, which made for very exciting science when we were all stuck at home during the pandemic. Okay, I'm going to start with a bit of background just to bring you all up to speed so that you're all ozone experts before I get into the fun stuff. Ozone is a simple allotrope of oxygen. It's three oxygen atoms. Oops, wrong. Three oxygen atoms together. It's formed by the action of ultraviolet radiation from the sun on oxygen in the upper atmosphere. Some of the individual atoms, after dissociation by short wavelength ultraviolet radiation, combine with oxygen to form ozone. There's a cycling back. These reactions are actually not important. I'll talk about the ones that really work later. But this was the original mechanism that was proposed about 100 years ago. And the top part of it's correct. So ozone is continuously formed by the action of ultraviolet radiation on the upper atmosphere, mostly around the tropics. And the other things I want to tell you are that right now are that it had ozone absorbed strongly in the ultraviolet at several different regions, also in the infrared and in the visible. These are the important absorption bands here. And it's also highly reactive, which means it gets involved in all kinds of things in the atmosphere, and and that is why it is so important and why it can be measured in so many different ways. But I won't talk about that really till tomorrow. So simple here, the structure of the atmosphere, which I'm showing here, a typical ozone profile. So there's more ozone up here around 25 kilometers, which is why we call it the ozone layer. Most of the, about 90% of the ozone above our heads is in the stratosphere, and about 10% of it is down here where we live. And I've shown little schematics. That's where our highest balloons typically go, about 30 some kilometers. This is where planes fly, at least when the transatlantic ones get higher around the tropopause. And
Well, it is produced up here from the action of solar radiation. Down here, there is a strong contribution from chemical reactions in the atmosphere, which are we call pollution. So, but you can see that because of ozone, the atmosphere has a permanent inversion layer. So ozone is actually responsible for the temperature structure of the atmosphere. No, yeah. Oops. Okay, I think that's what's supposed to be next. What happened? Yeah, okay. So, as I said, ozone's mostly formed here. Up in the upper atmosphere, 25 to 40 kilometers over the tropics, and then it is pushed towards the poles by the wave-driven circulation which we call the Brewer-Dobson circulation. After Alan Brewer, who was a professor here, and Dobson, who was his predecessor in ozone science in the UK. Actually, Brewer started in the UK as well, before the big area. So I've got here, this is a measurements from the satellite way back when, but it still looks the same. The highest concentrations of ozone are here, where the atmosphere is fairly thin. The circulation moves it downward and forward. This is the average slow circulation, takes years from the tropics to the poles. And that pumps it. So we end up actually with more ozone over our heads in Toronto than you have over the tropics, simply because there is, of course, a lot more air here. And the ozone is lower down. So the same concentration leads to a greater absolute amount of ozone. There are a lot of dynamic processes which are shown in that schematic, but I can't go into them all. But just this slide is just to demonstrate that what I was talking about a little more clearly. You see that ozone, this is the total column of ozone. So the total amount of ozone between us and space. And you can see that it is down around 250, 300 Dobson units in the tropics, but up to around 400 in the spring in the northern hemisphere. And that is typical. And in November, you see the opposite because the circulation is this is the spring. In November, it's spring in the tropics, and the circulation is a little stronger in spring. These graphs demonstrate now these are annual averages of March total ozone temperatures and a measure of the flux of wave-driven flux of energy towards the poles. So, so ozone's a renewable resource. If you were able to wave a magic wand and make all of the ozone disappear, the sun would reproduce the amount that we have in about 10 days. It's produced rapidly. It's also destroyed rapidly by photochemical reactions in the atmosphere and primarily over the tropics, of course. But the Brewer-Dobson circulation also brings it away from its source regions towards the poles, towards mid-latitudes. So in this analogy of a leaky bucket, I think, works quite well for understanding that. You've got the sun, constant production, and and the bird ops in circulation, bringing it over our heads. But you've also got loss reactions. And it turns out what Chapman proposed 100 years ago is not the major loss reaction. Loss reactions are mostly from NOx, oxides of nitrogen, oxides of hydrogen, chlorine, and bromine. And of course, you've all heard about chlorine, chlorofluorocarbons. But originally, before that, we were worried about nitric oxide more than anything. But all of these contribute to reactions that reduce the amount of ozone. And so the amount of ozone over our heads is a complicated balance between dynamics, the bird ops in circulation, bringing it from a relatively constant source, sun, and its loss reactions. So when we talk about ozone depletion being a problem, we're not talking about it all going away. When we talk about chlorine destroying ozone, the small amounts of chlorine, because the reactions are catalytic and the chlorine gets see what happens here. The chlorine in this reaction, the chlorine or the bromine or the nitric oxide is re-released so these reactions happen over and over again. That small amount of these chemicals can create a relatively large leak. But the sum total of all those leaks is what determines the amount of ozone over our heads. The other point that I want everybody to be familiar with is ozone is an incredibly strong absorber of ultraviolet radiation. What I'm showing here is this is the spectrum, a measured solar spectrum above the atmosphere. You can see it's relatively constant with wavelength in the ultraviolet region here that I'm showing. This is, these are actually two, they fall almost on top of one another, spectra measured by a Brewer ozone spectrophotometer, the kind we use all over Canada and most of the world now. And so the ultraviolet radiation has dropped at these, if you look around 295 nanometers, it's dropped by 4 orders of magnitude. So even though there's only a small relative, ozone is a trace constituent of the atmosphere, it absorbs virtually all of the short wavelength radiation. And in fact, once you get below about 293, we can't even measure the amount of ozone there, even with a photomultiplier based instrument like the Brewer. Another way in which ozone is really important is in radiative forcing the atmosphere. Ozone, as I mentioned, is a strong absorption. It absorbs in the infrared as well as the ultraviolet. Here we're concerned primarily about its infrared absorption. These are a couple of calculations showing the effect of a 10 Dobson unit or a 10% change in ozone or ozone in the atmospheric column. So ozone is, I think, well, if you don't count water vapor, it's the third most important climate forcing gas in the atmosphere. CO2, methane, and then ozone. Ozone is also really important, although we don't, actually hasn't been a lot of research in Canada on this. It's an important for agriculture. It's an important pollution with regard to agriculture because excuse me, it damages reduces crop productivity by quite a significant amount. This is a calculation that I got from made up from some Indian results. In India, it's much more of a problem where it's than here. But you can see that the most, well, the second most, I guess, after beans, yes, most susceptible species is wheat. Wheat's a $10 billion crop in Canada, so 10% reduction in wheat productivity is quite important. It's also, ozone is a is an irritant to human lungs. It's does respiratory damage, and well, you all know about that. Okay, that's a quick run through of all the reasons that of what we know about ozone and why we're concerned about it, why it's an environmental issue. But I want to talk about how we got there. Like, why do we know anything about ozone? We didn't start with an environmental issue. We wouldn't know there was an environmental issue if we hadn't already known quite a lot about it. And so I want to think about the relationship between science and society. And using ozone as an example, I submit that science starts with curiosity. Science that fundamentally it's about people saying, hey, look what happened when I did that. Or did you see that? I wonder why that happened. Think about the earliest science, astronomy. It started with shepherds who didn't have anything to do at night, right? There wasn't any, it wasn't Netflix. You looked at the stars and you naturally wondered what they were, where they were from, what caused them, what that was about. I mean, eventually people figured out that this would be a great way to navigate, but that was later. They started by wondering why some of them moved and some things changed. We all have one of these in our pockets. This would not exist if Faraday hadn't done experiments with electromagnetism and figured out a lot of the notions that we now understand about electricity. And it wouldn't exist if Bell hadn't been interested in trying to understand human speech and develop ways of working with it, which of course resulted in the telephone. It's all starts with wonder. And I think most of us, I mean, I certainly find that the most interesting things in my Google feed or what I read on this device are all about new scientific discoveries. I think fundamentally, I'm not sure that you'll all like this being scientists, but I think fundamentally we're entertainers. Now, the progress, of course, is non-linear. There are dead ends, there's zigzags. They don't usually end up in your textbooks where it all seems to be just A, B, C. But there's lots of stuff in between there. But it usually works something like this. I mean, it starts with interest, curiosity. Then you make observations. Sometimes there are immediate repercussions of those observations, like, hey, this star always stays in the same place. We could steer our ship by. So that, I mean, humans realized that thousands of years ago. But then later on, you want to know more. You develop models, theories, empirical, maybe now, of course, we think about computer models, but any type of theory is a model of our understanding. And that leads to directed measurements and applications, but that's all, this is developing the cell phone. We already know what we're doing at that point. But I think sometimes It's when we don't know what we're doing that we're doing our best work. Okay, so back to ozone. The the ancients were aware of the odor that you sometimes smell from a thunderstorm. Homer makes references both in the Odyssey and the Iliad to the smell of thunderbolts. Interestingly, the smell in literature varies, or the descriptions of it vary from clean, and some refer to a weak chlorine smell, some to sulfurous. I think the latter is perhaps the more of an association with Zeus than an actual observation. However, it seems that the clean smell, as people often describe it, before a storm, is probably ozone coming in downdrafts from the thunderstorm. However, after a rain, it's partly the smell of geosmin, which is a terpene released by soil bacteria. So actually has not a lot to do with ozone, but that's what you discover when you start delving into these things in more detail. There aren't a lot of measurements of how much ozone is produced by thunderstorms at the ground, however, probably because it's rather dangerous to make such measurements. But we know that lightning produces a lot in the middle atmosphere, but the measurements of increases at the ground seem to be in the order of 10 to 40 parts per billion. So that's roughly the amount that's likely in this room right now. So it's not very much of an increase. So I guess about the first mention, or first scientific measurement, if you like, of ozone is Van Maram's experiments in the late 18th century, where he talks about the odor of electricity. At that time, it was thought to be an electrical effect. And modern studies suggest that the amount of ozone, the lowest amount of ozone that we can detect with our noses is around 10 to 50 parts per billion, which is, again, typical amounts for the atmosphere that we normally breathe. So in 1840, Schonbein, who's often described as the first or the discoverer of ozone, because he recognized or hypothesized that this was a gas. And you'll note that the name of his paper, On the Odor Accompanying Electricity. So the human nose was the scientific instrument of choice for about the first 10 years. And there are lots of, the early papers all talk about the smell, because that was the only way we had to detect it. However, by 1845, he developed a method involving the reaction of ozone with potassium iodide on starch-impregnated paper strips, which allowed a qualitative measure of ozone. There was a lot of interest in the 19th century about this, so there was fairly rapid advancement. We have, as I've listed here, a suggestion that ozone is a form of oxygen. Olding suggests that it's O3. And by 1868, Soré was able to demonstrate that ozone was an allotropic form of oxygen, O3 rather than O2, by quantitative laboratory measurements. And quite importantly, Houzeau developed a quantitative method which and showed that ozone's present in natural air. And that's important because Schonbein's papers were not very sensitive. So by 1858, we have Schonbein declaring that ozone exists in two forms, that there was ozone and antozone. And so for about a dozen years, there was a lot of debate, and there are lots of papers about antozone. But by 1870, it was established that what they were really looking at was hydrogen peroxide, and which is of course an oxidant related, which can relate to ozone, but it's not an opposite form, as he had suggested. But what I found most interesting was how many scientists in the 19th century, people you know from other areas like Becquerel and Faraday, who published on ozone. Like, it was definitely the hot topic of the 19th century. This monograph, which you can actually find online. I just downloaded it. 1873 has lots of fascinating statements. I liked the line that Fox says that ozone was used in America for the destruction of the empyreumatic taste of whiskey. Any Greek scholars in the audience? Okay, that means smoky. I love 19th century writing. It's so great. Anyway, he alarmingly goes on to suggest that decomposing and putrid animal food could be restored to wholesome freshness and purity by the employment of ozone. That one seems a bit doubtful to me. I don't think I'd go for that. Certainly true that it's a deodorizing and purifying agent. I mean, it's highly reactive. It's a very strong oxidant. So it tends to destroy any organic molecules in its path. Yeah, the third one is perhaps a good idea, but I love the fourth one. Ozone's a great bleaching agent with whose effect all laundresses are acquainted, and the tanning influence of which is deplored by young ladies, especially during a sojourn at the seaside. Of course, it was not fashionable to be tanned in the 19th century. White skin was prized. That's why they all carried parasols. But of course, this is all quite wrong, because we know it's UV radiation that causes tanning and causes the bleaching. If you put your sheets out in the sun, they do get bleached, but it's UV radiation. But they had made the association between the clean smell of the ocean and ozone. And by the way, the clean smell of the ocean is probably dimethyl sulfide. So which is again another chemical yet again. So it suggests that the human nose is not very discerning. It can detect ozone or something. But at the time, mountain air was thought to be very healthy. There were loads and loads of resorts. Actually, there's still some I found on the internet advertising that they have lots of ozone, and you should come there because they're up in the mountains. You do tend to have higher ozone in higher altitudes. But so yeah, Beaumont, California in the 19th century had adopted the slogan "Zone of Ozone," trying to attract tourists. So, and I've decorated these slides with a couple of the designs. There are many of these in Fox's book. There are a variety of enclosures that were built to try and make the Schoenbein papers more accurate. Everybody was using these Schoenbein papers, which were kind of like litmus. They look like litmus papers, but they changed various shades of purple depending on their exposure to ozone. And as it turns out, a whole lot of other things, but we didn't know that at the time. So there's some interesting things here. This one. Section of an ozone box made for Dr. Mitchell by an Algerian Arab. Wasn't thought to be important to mention who he was. He was just, the casual racism that one encounters is kind of disturbing. And there's another one at the top. anyway, measurements were with these Schoenbein papers are made all over the world. We have thousands and thousands of them. There are many different boxes to try and make the measurements more to control the airflow and therefore make the measurements more representative. They learned a lot during this time. The harmful effects on animals were documented. First disinfection plant using ozone was started in 1893. And the Fox monograph describes observations that ozone was apparently generated by plants. Don't know how they got that idea, because it's not. But counter suggestions that it was due to reactions with volatile organic hydrocarbons, so which in fact it is. And in fact, terpenes that come out of conifers are sources of volatile organic hydrocarbons. So maybe those weren't so far apart as it seems now. So there are many aspects of ozone distribution and variation that were noted using the Schoenbein papers that are regarded as valid today. But there were many wrong turns as well. The next most important thing I want to mention is the Montsouris ozone measurements. There was a quantitative measurement using potassium iodide to actually measure ozone. And these were carried out at the Montsouris Public Health Laboratory on the outskirts of Paris for about 30 years. And so we still have those data. And I was able to reanalyze them myself some years ago. And I found also that they had made measurements of ammonia and sulfate and nitric acid in rainwater, which turned out to be quite useful to me. But now, that's ozone, and we're still talking there about ozone at the surface. I want to go back to where we were talking about ozone in the upper atmosphere, in the stratosphere. Well, at this point, we don't know where it is actually. The Cornu observed that solar radiation cuts off about 300 nanometers. And you just don't get any UV beyond that. And in 1881, Hartley measured the ozone cross-section in the laboratory and showed that that this cutoff was produced by ozone. So basically, the information that I showed you with that slide a while back, this very sharp cutoff is this is a logarithmic scale. Right? Each graduation here is a factor of 10. So if I were to plot this on a linear scale, it would just go like that. The intensity of solar radiation is falling off a cliff. And an experiment by Strutt, who I think was it's not the famous Rayleigh, I think that's his son. Showed that the absorption was not happening in the lower atmosphere. He did a long path measurement and showed that kind of absorption had to be happening elsewhere in the atmosphere. So at this point, we know that it's up there. And there was a report by Huggins, an astronomer, that absorption bands absorption bands in the spectrum of the star Sirius, which is the brightest star in the northern sky, southern sky, yeah, were due to ozone, and the observation by Fowler and Strutt, or the attribution of those to ozone, and finally more careful measurements by Fabry and Buisson, whose apparatus actually we see in this picture here, picture from 1928, so almost 100 years ago. You'll notice the modern equipment. That the total amount of ozone thickness was about three, what we now call Dobson units, 300 Dobson units, 3 millimeters. In other words, if we brought all of the ozone down to atmospheric level and concentrated, it would form a layer 3 millimeters thick. So then ozone measurements in Canada start about 1935. This is one of the first spectrometers built by Dobson. It's actually made of wood. There were photographic plates initially. This one I think has had, I think the plates have been were replaced by a photoelectric device, but originally it was photographic plates. And Dobson actually made a small network and discovered some important aspects of the distribution of ozone around the Earth. By this later instrument, which is what we usually call a Dobson spectrometer, was developed a few years later, and there are hundreds of them around the world there that are still in use. We don't use them in Canada anymore because of the development of Burr. And I mentioned the Burr-Dobson circulation. Burr actually deduced that from measurements of water vapor in the tropics. And but we now know that that is the principal circulation of ozone in the atmosphere. So leaping forward, the International Geophysical Year in 1957, most of the global network of ozone measurements was established. There were Dobson spectrometers, like in the picture I showed you a moment ago, installed all over the world. We have several stations that started then in Canada. That would be Edmonton and Resolute, at least. But the interest in ozone then was as a tracer of atmospheric motion, where people were trying to understand how the atmosphere moved. This is the Burr-Dobson circulation that I've mentioned, but also whether it would be important to long-range weather forecasting. That was the thrust back then. And then Paul Crutzen showed that the major ozone loss in the stratosphere was through nitric oxide. And I mentioned that in my leaky bucket slide. That's one of the trace elements. Nitric oxide was thought to be the most important. And right about that time, some of you may remember, there was a proposal to build a fleet of supersonic transport aircraft. We were going from airplanes, which is all any of us likely have flown on, that fly at less than the speed of sound, to things like the Concorde, which was the only SST that was ever built in the end. But this fleet of SSTs was thought to be, was great concern because they would be pumping out nitric oxides right in the stratosphere where the ozone layer was, where it was most critical. So substantial ozone depletion was proposed. And then a couple of years later, Stolarski and Cicerone found that chlorine could do the same thing. And Molina and Rowland showed that CFCs, which until that time had been a miracle of chemistry, they were inert. They did absolutely nothing chemically. They were simply a mechanical, they were used for their mechanical properties. They were used in spray cans as a propellant. They were used in refrigerators and for plastic foaming and all kinds of uses like that. But simply for their mechanical properties. And what Molina and Rowland showed was that if they drifted above the ozone layer where you didn't have that cutoff of UV radiation, they could be broken up and release free chlorine. So now there's huge concern in the 70s about what's going to happen. And this is kind of an interesting plot that I dug out of an old report. It shows the projected loss of ozone, that's this scale here, based on by year, based on the development of atmospheric models. So as atmospheric models become more refined with time, the prediction goes up and down. So here in the early 70s, we're predicting large losses. And one of these curves is from NOx from stratospheric aircraft, and this one is from CFCs. So large losses, and getting even larger here from CFCs, but gone the other way from NOx, and then down here getting close to more modest amounts here. So the problem, I don't know if some of you who are old enough to remember would remember that there was great concern, and then there wasn't so much concern, and then there was great concern again. It's basically following this graph. I remember how it seemed to wane, to wax and wane, and it's because the latest results were sometimes showing, oh, this isn't such a big problem as we thought. Well, as it turned out, chlorine and NOx, although they're both very strong, very important loss species for ozone, they like combining with each other better. And they tend to form chlorine nitrate and hydrochloric acid through these reactions here. And these species we call reservoir species because they don't do anything in the atmosphere. And so the end result of all of the graph I just showed you until 1985, you know that, yeah, it only goes up to about 1986, was that it isn't such a big problem. There may be a few percent loss of ozone. That's what we're seeing here. Because of these reactions that take the chlorine and the NOx out of service. And then there was a discovery of very odd changes in the Antarctic stratosphere. And it turns out that it's due to these very pretty noctilucent clouds. They light up at night, they're in the stratosphere, and they're made of nitric acid trihydrate ice. And in the extreme cold and dark of the Antarctic stratosphere, these reservoir species get processed on, this is exotic chemistry, on the surfaces of these nitric acid trihydrate particles. This isn't happening in the gas phase. That's what we call mixed phase, heterogeneous chemistry. And these process chlorine into forms that are easily photolyzed. So then when the sun comes up, the clouds evaporate, and there's 100 times as much free chlorine as there would be. And it starts gobbling up ozone. And this is a picture, a graphic of the Antarctic ozone hole, really the first one we saw in 1985. So, yeah, these observations were at that time made from the ground. NASA mounted the Antarctic Airborne Stratospheric Experiment. Susan Solomon suggests in 1987 that this exotic chemistry is happening on the nitric acid trihydrate ice particles. There were a couple of more airborne experiments, and within a very short time, it was demonstrated that this strange chemistry was what was causing the ozone hole. At the same time, interest in ozone, that concern about ozone that had been happening for the previous 15 years led to the Vienna Convention, which Canada was the first signatory to. And the resulting Montreal Protocol to limit and eventually ban CFC production. And then a little later, we developed the UV index, which you can, that's slightly slides above the UV index. Here we Global Environment Canada forecast, and these are measurements made with the Brewer spectrophotometer. This one is that's Regina. So these are estimated clear sky UV is the purple line. This is the climatology smooth curve, and these are daily maximum measurements, which generally fall below the clear sky because, of course, clouds tend to block UV. So anyway, you all know about that. But at the same time, or perhaps going back a little bit, the down in the troposphere, that's the atmosphere down here, the part we live in, there were large amounts of ozone being observed in under certain conditions, in particular in Los Angeles, the famous smog incidents, which were demonstrated by Hagen-Smith in 1952 to be ozone. Initially, they were thought to be sulfur dioxide, which people were familiar with from the even as far back as the 19th century. But Hagen-Smith and co-workers observed as much as, well, typically over 600 parts per billion, which is 20 times what we would consider normal now. And there are measurements as high as 1,000 parts per billion from Los Angeles at the time. Another interesting development, sort of in between the stratosphere and troposphere, in the early 1970s, aircraft started to fly higher and a little further north. The new long-range Boeing 747, in particular, was following more northern pattern flight paths and flying higher, so that it was commonly in the lower stratosphere, going above the troposphere. So ozone levels go up very rapidly once you get into the stratosphere, and they were observing cabin levels as high as 1,200 parts per billion. These are lethal, well, potentially lethal levels for humans. And the story of how they discovered this is kind of amusing too. They at the time, NOAA, the National Oceanic and Atmospheric Administration of the States, was trying to encourage university professors who were just starting out in their careers to consider careers in atmospheric science. And so they've been given some funding, a couple of my now retired colleagues, to go around and make presentations. And so they had some ozone meters and so on with them. And anyway, long flights are boring, and the airplanes used to have those little nozzles. Some of the older ones still do, with a little hole in the middle. They look kind of like an eyeball, and you twist them around to make the air blow in your face or not. Well, they noticed that the hose, the inlet hose for their ozone meter, was the same size as the hole. And so they went, well, I have a hose, I have a hole, so yeah. And so they stuck it in there, and then they went, well, holy shucks, or something. There's a lot of ozone coming out of there. So they told Boeing about it, who immediately freaked out and said, "How much money do you need? Here's a blank check. Fix it." And so that's how the Global Atmospheric Sampling Program started in 1974. They had carte blanche to measure whatever they wanted, whenever. And out of that comes current regulations on ozone in cabins, which is why all airplanes have scrubbers. But scrubbers are not actually required. It's still okay, according to the regulations, to try and fly around the high ozone. because in the 1970s, people thought you could. And if you actually pull these up, they're on the internet. You can see like a hand-drawn profile from some of the early ozone sonde flights that's illustrating the FAA regulations, and the Canadian ones are basically copied from there. So I actually got a call a few years ago from Bombardier. They were producing a new regional jet, and they wanted to know could I give them really better ozone maps, and how feasible was it to go around the ozone? And I said, no, you can't. That won't work. But more recent measurements on airplanes have shown that they regularly exceed the rather generous guidelines for ozone. We start shutting down industry when ozone hits 100 parts per billion in the city. On the airplane, that's just considered normal. And you can go up to 250 before it's supposed to be bad. But anyway, they regularly exceed that. Other measurements at the time, they're occasional, mostly in Europe, in the mountains. This is Paul Goetz. Looks like he needs snowshoes. And he's making a long path measurement at Arosa in Switzerland. And then this paper came out. These guys had analyzed some 30 years of measurements at a bunch of stations in East Germany. And doesn't look like a very exciting graph. But if you look at it here, it doesn't display it very well either. But ozone appears to have doubled average amounts down here to around here, almost doubled over the period of measurement. And then this is Bojkov, who was, I think, a Canadian at that time. He did work in Arctic Canada. This is from our ozone sondes in Resolute in the 70s. And a couple of other stations here. He's getting a similar trend. Ozone seems to have doubled. So, also coincidentally, Kurtzen had pointed out that photochemistry could be the major source of tropospheric ozone. And as I mentioned, the very scary amounts of ozone in Los Angeles were clearly empirical evidence for this. There were some attempts to calibrate the Schoenbein papers to try and figure out what ozone had been in the 19th century, to try and get a sense of whether it was increasing drastically like this. Bojkov used the Montsouris measurements, that public health laboratory near Paris that I mentioned, to calibrate the Schoenbein papers. And also Volz and Clay showed they actually built the Montsouris apparatus from 100 years earlier, and they demonstrated that it was accurate. And they estimated that the Montsouris results showed that ozone had been around 11 parts per billion in the late 19th century. So that meant there was a drastic increase. And this all made sense with industrial development and, the idea that there was more pollution in the atmosphere. And you had papers like this showing, this is an attempt to try and put all these measurements together, including some modern measurements with, I think, with Schoenbein papers. Anyway, this suggested that ozone had increased by a factor of 5. So this is about when I started in Environment Canada. Everyone knew that tropospheric ozone was going up rapidly, and it was a big problem, and what we were going to do about it. And David Parrish, who was a very prominent chemist, atmospheric chemist at NOAA, published quite a few papers looking at older data and comparing it to more recent data, and argued that ozone had increased by at least a factor of 2 or 3. But climate models couldn't reproduce that. And they tried, and eventually they modelers don't like to tell you that your data is wrong. That's considered at best impolite, but they would say, they would say privately that, well, there's no way this can be right unless trees weren't producing isoprene in the 19th century. They couldn't figure it out. So with some colleagues, I went back and looked at this. And one of the things I first noticed was that there were experiments from way back when. This is 1980, it's 1988, showing that the Schoenbein papers, these litmus papers, on which all that data from the 19th century is about, were more responsive to humidity. That's what this curve is about. It shows stronger dependence on relative humidity than they do on ozone.
I apologize to interrupt you. I just to give a little time warning. It's now just past
Oh, yes.
3. So we can wrap up in the next few minutes.
And this experiment showed that it showed that they actually had a very strong dependence on how long the measurement was. But this was ignored by the other people. In the conclusion I mentioned, where everything seemed to point to ozone was going up very rapidly. So when we went through all this, we found that there was strong interference from sulfur dioxide in the 19th century and enormous dependence on the conditions under which the measurements were made. And more interestingly, some of the older documents say the same thing. More than 100 years ago, Fox and Hartley had drawn the same conclusions, that the Schoenbein papers were completely unreliable. That left us with the Montsouris measurements. Volz and Clay showed that the instrument was accurate. However, they estimate 2 to 5 ppb of SO2 interference. SO2 interferes with the potassium iodide measurement method. We're quite strong. Well, if you look at the conditions, Paris in that time, there are so many interference that would be expected, and indeed were measured at the observatory. Those measurements of nitrate and sulfate in rainwater translate to huge amounts of SO2. In fact, I can't understand why they measured any ozone at all. They should have got 0 all of the time. And amusingly, we discover in Hartley's 1881 paper that he also dismisses the Montsouris observations as being urban, not country air. So when we do that, when we take all that into account, we have these older measurements, some of them made by long path ultraviolet spectroscopy, some of them made with potassium iodide, various measurement methods related to or using the potassium iodide reaction. And we have an increase of about 50% when we go to modern measurements on surface. And when we look at early balloon and aircraft measurements, that's all these here, we'll find the same thing. The increase is about 50%, which happens to match quite neatly what the modelers find. It stopped.
If you would escape.
No. Right. Oh dear. No. It says screens sharing has stopped. Yeah, I think so. Good. Okay. So very quickly, this is what modern ozone measurements look like in Canada. We have networks of the red diamonds are showing the surface measurements made through two networks run by Environment Canada. I think actually the provinces are involved as well. The Brewer ozone, total ozone spectrophotometers here and ozone sondes. So and there are similar networks around the world. I mentioned the Montreal Protocol. Measurements show that CFCs in the atmosphere are indeed decreasing. They peaked around the turn of the century, and they are measurably going down. So the protocol is working. And so we expect ozone to go back to normal levels slowly, but I mean, these won't go down to nothing, to negligible amounts for about another 25 years. There we are. But in 2020, we had this over the Arctic, a decrease, severe loss of ozone, very similar to what we see in the Antarctic. And in fact, if we look at it in detail, these are our ozone sondes from Eureka, which is one of those stations at a little over 80 degrees north. This is the typical amount we see in February and March. This is what happened in the 2011 severe losses, which were at that time, I think, suggested that was an ozone hole. And then we told that's not really a hole, it's not big enough. A little. So this is what we got. These curves here are the most severe depletion we've got in 2020. And they look remarkably like the Antarctic profiles. And indeed, we're down here. Here's the temperature for formation of those polar stratospheric clouds, that where we get the hydrogenous chemistry of use of chlorine. And so here's typical temperatures for the Antarctic, and you can see that in these years, especially in 2020, we're getting right into that agreement. This light gray is the typical temperatures for the Arctic. So we had a very strong, very cold, very tight polar vortex, and that led to severe depletion. So the interesting question is, how much in the future is this going to affect the recovery of stratospheric ozone? And so these, I'll just leave you with these conclusions. We expect that the Montreal Protocol is working, and we will continue to see overall an increase of ozone, average ozone over our heads. However, data don't show this yet. We expect that climate change, by cooling the stratosphere, will cause future ozone holes. And then there are questions, which I think interesting questions. The most practical method for dealing with climate change in the short term is to put dust in the stratosphere. But we know from volcanic reactions or volcanic eruptions, like the large one we had 20 years ago in Mount Pinatubo, 30 years ago, that while that cools the Earth, it also causes ozone depletion. There's also a lot of concern about rockets. The number of rocket launches is increasing exponentially because of satellite constellation launches like Starlink and so on. And climate change will probably increase ozone in the troposphere. for a number of reasons, including forest fires. So I'll stop there. I'm sorry that I ran over time.
Mentioned that most of the observations are questionable because of the condition. Do we, based on what we now understand from the Chambon papers, do you have any sense as to what tropospheric ozone levels were like in the 19th century?
Yeah, they're about 20 to 25 ppb. That's one of the things I found most interesting is once I went back before Bozkov and others got this on this bandwagon of tropospheric ozones going up. It's a huge increase and so on. That all the 19th century observations it's around 20 to 25 ppb. In fact, nobody even thought it was very interesting because the measurements were all about the same. Thanks.
Is there anything online?
Okay, so we have the Montreal Protocol. That's the world's the most successful international agreement to date.
Arguably, yes.
Arguably, I believe Kofian.
I'll be making that argument in
Sorry, I
Say yes.
So we have that for stratospheric ozone. What do we do for tropospheric ozone? Is that a local or regional or a state problem? So there's no real.
Both actually, because ozone in the troposphere is relatively long-lived. It has an average life. I mean, it varies quite a bit depending on where you are, but the average lifetime is 3 to 4 weeks. So I have a plot I can show you of estimated contributions at a station in Ireland, I think it was Victor Irwin's plot. But you see that there's contributions from local production, from stratospheric intrusions, from production that on the other side of the world, and indeed some that's gone all the way around the world. So even though particulate matter is a greater health concern, actually, ozone is a concern for regional transport. Particulate matter tends to be rained out very quickly, so it's local. And you don't have to worry about what they're making in Alberta or in China. But ozone from China comes here.
So do you see this as being the next place for international agreements or treaties?
Well, I think we're all working on that. Certainly working on trying to understand it and measure it better. Yeah, it's a lot of work being done in China. Some interesting results that some of my colleagues there have made. Yeah.
Thank you very much.
So in the early 70s, there was this interest in leader supersonic aircraft that spurred a lot of this interest in ozone. And then I remember when I started graduate school in the early 90s, there was more interest in building another fleet of supersonic aircraft.
In the 90s?
Yeah, no, there was some interest there that people were, but it didn't go in. And then there was some discussion that we might finally do that in around the mid 2000s, but then there was the 2008 crash and the aircraft industry just abandoned the idea of doing this. And again, I'm hearing talks about.
I've heard that they're talking about it again. Yeah,
exactly. So where do we stand in terms of the potential impact of such a fleet of aircraft on the stratosphere?
I don't think anybody's terribly worried about the NOx because we found that it reacts with the chlorine and they sort of take each other out of circulation. Now, if you remove all the chlorine and then you put stratospheric aircraft in there, I guess that becomes a problem again. So maybe we'll have to put more CFCs in the atmosphere in order to fix the ozone layer.
So we have a question that asks, could you discuss how CFC manufacturers reacted to the observational discoveries of ozone hole?
The usual way. We need more research. It isn't proven yet, and we don't know if changes, there was a paper, Scotto et al., that was notorious for a while that seemed to show that ozone changes did not relate to UV changes. And eventually, that was shown to be poor data quality control and so on. But my impression is, and I can't prove this, okay, this is just my opinion. So, but it seemed to me that we went from industry was no, this is just you guys have got it wrong, or it's not, to suddenly they were on board. And I think what happened is that the chemical companies realized that they could make way more money off of the substitutes for CFCs, because HCFCs were like 4 times as expensive. CFCs are cheap, but HCFCs are about 4 times as expensive. And so because opposition just suddenly disappeared. There wasn't never anybody coming up to me at conferences and saying, no, it's all nonsense. They just weren't there anymore. It was all fine. Yep, we got to get rid of those CFCs, and everybody's got to change over to buy new air conditioners that run on HCFCs. Then we have to change them again and get rid of the HCFCs. So yeah, everybody made money. So it was all good. So unfortunately, that didn't happen with the Kyoto Protocol. Nobody's figured out a substitute for fossil fuels. That one was always going to be harder. Everyone knew that. John?
Oh, yeah, it was really fun talk. I wouldn't recommend this, but as someone who used to work with those in the lab a lot, you can smell it, and if it passes over your hand, and you wave your hand around, all the ozone should be gone, right? It's gas, but you still smell it. You smell your skin. I've always wondered the smell of ozone is due to the oxidation products that come off your skin when you smell it.
I have no idea.
I don't either, but this reminded me of it.
Yeah.
This talk, it was a beautiful talk.
Oh, thank you. I had a lot of fun digging into the old references, and I had for years said that the smell of lightning was ozone. And then I found out apparently it's not. It's this terpene that's emitted by bacteria after a rain, and on the ocean it's dimethyl sulfide. So apparently we smell lots of different things. Go, oh, that's ozone. I can't smell anything anymore. I lost my sense of smell, so I have to just take it by hearsay.
That might be an interesting place to end it. So please join me in thanking Dr. Tarasick. Please come back tomorrow for the next lecture at 11 o'clock. Same room,